All right, well, welcome everyone to our weekly Wednesday webinar series. As always, we do our courses live and then they're available on demand anytime within our YouTube channel, USGBC education channel, and other platforms. I'm really excited about this session today, a net zero case study on design, construction, and lessons learned. The reality is even that this home we're going to be covering today was built over a decade ago. The sort of bittersweet thing is that even today's codes have not even caught up to the level of efficiency of a home like this. And so in some regards, it's great to be able to go back and take a look at how these homes are performing and help hopefully influence even the way we're building today to meet these more sustainable standards. Now, before we get started, I want to say a huge thanks to our Platinum Plus sponsors, Rheem. They make heat pump water heaters, which are the future of water heating. They take heat right out of the air and then use it to heat water with zero emissions directly up to 400% efficiency. They offer a hybrid water heater with backup resistance at 240 volts to ensure hot water all the time, and 120 volt systems that quickly replace gas systems without the expensive electrical upgrades. They work by pulling that heated air through the filter. It's absorbed by an R410 refrigerant using a compressor to heat coils wrapped around the tank. They've got control systems in place to monitor energy usage or alert or leaks. And the Inflation Reduction Act tax credits now up to potentially $2,000 or 30% of the cost, and $600 for electrical systems improvements that you might need to install these systems. Don't have the space or availability to do a heat pump water heater. They have standard electric resistance that have time of use demand response programming built right in. Check them out over at rheem.com/heat pump water heaters. And also a huge thanks to our second tier sponsor, Panasonic Ventilation, who's offering many different ventilation solutions from basic needed code requirement all the way up to heat recovery and demand controlled. Check them out over at Panasonic Ventilation. All right, this session is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We are a small but mighty team, and I will be your moderator today. My name is Brett Little. I am the education manager here. This course is approved for multiple continuing education CEUs, including our certified Green Home Professional designation in energy and health. AIA Health, Welfare, and Safety make it applicable to your state-based design or contractor license. And you can pick up your FIAS code, which will be sent out at the end of the course as well. All right, well, I am excited to welcome our speaker here today, Jim Riggins, the homeowner of this project, who's going to take us through his experience with design, construction, and lessons learned with the home. So, Jim, welcome, and please do take it away.
Hey, thanks, Brett. I was just going to ask you if you could stop sharing so I could bring up my slides here. All right, well, welcome everybody. We're going to cover a lot of ground today, so I want to jump right into this. Just real quick about my background. After retirement from the Air Force as a research engineer and pilot, I got my ratings at ResNet as a home energy rater and BPI as a building analyst, and ran my own business, Center Smart Energy Solutions, for a number of years, doing residential commercial energy audits, Energy Star certifications, and also EPA WaterSense certifications. Today, though, I'm going to talk about the design and the performance of our house in Monument, Colorado. This should be fairly obvious to this particular crowd, but why net zero? According to the Energy Information Agency, about somewhere between 30–42% of the total energy consumed in the country is in commercial and residential buildings. So building in a much more efficient manner and being able to retrofit older buildings to higher energy efficiency is going to be critical to minimizing carbon footprint overall for the nation. So jumping into our house, this is what my wife and I were looking at when we sat down and started planning out the design of our permanent retirement home. We were looking for sustainable construction, maximum use of recycled material and maximum use of recyclable material. We followed the passive house philosophy and actually used the passive house model, although ultimately I did not get passive house certification for this. We are Energy Star certified. Net zero can carry a lot of different definitions. Our particular definition for net zero was we would not use any combustible fossil fuels in the house, so no natural gas, and we would be grid tied using solar PV, but we wanted to produce as much or more energy than we were consuming, and so that was the all electric aspect of the house. Some additional considerations: we were building very close to a urban wildland interface, and so wildfire resistance was of key importance to us. We also live in high desert, so water consumption and maximizing water efficiency was critical, as was high indoor air quality and the ultimate destroyer of homes, which is moisture damage. We wanted a high resistance to that. Getting started was very simply asking the first question of how feasible is this at 7,100 feet in Monument, Colorado, in climate zone 5, with over 6,300 heating degree days. So performing a simple bioclimatic analysis showed that, no surprise, this area would be a excellent candidate for passive cooling, with summers that have cool evenings and very low humidity. But that heating would be passive heating would be somewhat more of a challenge. We started, rather than designing a floor plan from scratch, we stumbled upon in our internet research a fantastic resource, which is the architect Deborah Rucker Coleman, who owns and operates sunplans.com. So we ordered a set of plans from her. She's one of the nation's leading architects that specializes in passive solar design. And so we started with a floor plan from Sun Plans that we then modified from a very efficient home to a net zero home. So that required a lot of modification to the shell, but we stuck with the floor plan. So we also focused on maximizing passive solar for the space heating, which we calculated to be about 44% of total energy use for standard homes in this area. So that was the low-hanging fruit, was to heat the house with as much ambient energy as possible. We opted for a slab on grade so that we could have a 4-inch concrete slab as our thermal mass on the main floor. and also looking at a fairly simple rectangular box design to maximize the volume to surface area ratio of the house. Uh, and finally, we were looking at an optimal south-facing roof pitch for both the solar PV and the solar hot water systems. And I'll talk more about that in a little bit here. The design process, which took over a year, involved a lot of modeling. So at the time, there were no if for those of you familiar with Department of Energy models like BE-Opt, there were no standard DOE models that were hourly models that could capture the impact of passive solar. So we used a commercial product called Energy 10, which was one of the few models that did do hourly modeling over 365 days a year. So what I'm going to show you on the next few slides is the parametric analysis that we did to design the house. So we built first in the model a reference home, first using just the code at the time, which was 2x4s. Ultimately, I built a higher performance reference home using 2x6 construction, which again was not even required by code at the time, and R19 insulation. And then from that standard baseline home where we calculated the total annual energy consumption, I would change one parameter at a time: walls, roof, foundation, windows. And you'll see these in the next few slides. And what we looked for was the knee of the curve, the bend of the curve, where we started to reach the point of diminishing returns. We're adding additional R value or U factor for the windows was not providing a an enormous amount of additional savings, either in energy or in cost. So that's the background of the parametric analysis. So starting with the walls, we modeled a number of options, just a standard 2x4 frame, structural insulating panels of different thicknesses, a 2x6 hybrid wall with fiberglass interior insulation and 1-inch exterior foam. Ultimately, though, the wall model that we picked was also a hybrid, but it was a 12-inch wide double stud wall, so it provides a thermal break. With 3 inches of closed cell spray foam. I'll talk about that in just a second. And then the additional 9 inches of blown fiberglass in the wall cavity. Also, in the wall model, we used advanced framing techniques: 24-inch on center, double stud corners, insulated headers, minimal jack, king, and cripple studs, and ladder framing where interior walls meet the exterior walls. Basically, what all that means is a framing option that minimizes the amount of wood and maximizes the amount of insulation. Now, going back to talk about the use of the closed cell spray foam versus other options in the wall, in addition to the fiberglass. One of the other really critical analyses that we performed is a temperature dew point profile through the wall. And the temperature dew point profile takes 25 years worth of climate data and assesses the risk that condensation will form inside a wall cavity and could potentially cause moisture rot or mold in the cavity. When you get in our climate zone with our temperatures, when we get beyond about a 2x6 wall thicker than that, the risk increases. And so one way to address that is to protect the interior face of the exterior sheathing with a vapor impermeable barrier. And closed cell spray foam at a thickness of approximately 2 inches or greater gives you a vapor impermeable barrier. Open cell spray foam does not. So that was one of the other reasons for, other than air sealing, one of the other reasons for the closed cell spray foam was to minimize moisture damage in the wall cavity. This is what it looks like in reality as the house was going up. You can see the double stud wall, 2x6 exterior stud, 2-inch gap, and then a 2x4 stud. They were built on engineered, single engineered top plates and bottom plates so that it could be assembled horizontally and then just lifted up into place. And that technique actually worked out pretty well. It's the first time our framer had ever done anything like this, but he said it worked very well. Moving on to the roof, we were driven to a roof design of a parallel core truss because I wanted, first of all, an unvented attic so that I could put some mechanicals in the attic, but also to reduce the risk of wildfire damage. One of the common sources of homes lost in our area to wildfires over the last 10 to 15 years has been embers that have blown up into soffit vents and ignited the house from inside the attic. So actually ignited the house from inside out. So an unvented attic with a metal roof had significant wildfire defense. Just by the size of the span that was being covered, the parallel core truss turned out to be 18 inches wide, so that was the depth of our insulation. 5 inches of closed cell spray foam, and then the remainder blown fiberglass, and then covered with 5/8 inch drywall. So the other options we looked at were just a standard 2x10 rafter with fiberglass bat, and then structural insulated panels of both EPS, extruded polystyrene, or polyiso, urethane foam. But ultimately we went with this hybrid approach again of the spray foam plus the blown fiberglass. This is what it looks like after framing, prior to the closed cell spray foam being blown up against or sprayed up against the roof deck, the underside of the sheathing. And you can see how much room is available then for installing mechanicals in the attic. The foundation, again, we wanted the concrete slab on the main floor, 4-inch concrete slab, to be our primary thermal mass. And so one of the lessons learned in the 70s in the first passive solar homes in the country was dispelling the erroneous belief that the earth was a good insulator and that concrete slabs do not have to be insulated. And it turns out that a fair amount of energy is lost, thermal transmittance and conductance, into the soil. So the insulating the concrete slab is actually fairly critical. And so the way we did that was with 3 to 4 inches of foam underneath the slab, and then also around the excuse me, around the full perimeter. So basically, the concrete slab sits in a bathtub of foam and is thermally isolated, both from the stem wall and also from the earth. Uh, the last, just a couple of items that we added uh, to the walls. There's capillary breaks between the poured footing and the stem wall to prevent uh, moisture. Concrete it can actually wick moisture, can wick bulk water. So to prevent that from wicking up into the stem wall, there's a capillary break at the footing, and there's also a an aluminum termite shield between the stem wall and the framed wall. Primary reason for that is termites are known to bore through uh, rigid foam, through the polystyrene foam. They don't eat it, but they can bore through it, and so it's possible for termites to bore up from the soil through the foam and into the lumber if you don't have a termite shield. Um, so uh, what the modeling that we looked at was just with varying thicknesses of extruded polystyrene foam. Although ultimately we went with a urethane foam option. This is sprayed closed cell foam uh, being trimmed along the foundation before the framing starts. And here's my helper, my son at the time with his hard hat on. This little boy is now a wildland firefighter in California. So that shows you how long ago this photo was taken. Okay, windows. The most complicated analysis was the windows because all of the other analyses were single variable, changing the R value. Um, when you get to Windows, though, you're modeling dual variable. You're modeling both the solar heat gain coefficient for how much sunlight you're going to get at different times of the year, but you're also modeling the U factor, or the the thermal transmittance or resistance. Um, so the way we approached this one was looking at um, existing window options from various companies, and we just use those parameters uh, between dual pane and triple pane windows, various different low emissivity coating options, uh, and uh, this was a case. There were probably two major areas, this being one of them, where from the modeling, I could not make an economic argument for the option that we chose. But the option that we chose was one to absolutely maximize the performance of the house and minimize the thermal loss. So we went with a triple pane window from Accurate Doran Corporation in Ontario, Canada, with a specific low E coating. On the south face, the windows are low iron to maximize the solar heat gain coefficient. And in the rest of the house, they were not low iron. They were selected just to have the lowest U factor, or the highest performance, thermal performance. Um, and it turns out that if I was looking for the highest return on investment, a high performance dual pane window actually would have made more sense. But again, we intentionally opted to go with the more expensive windows for better performance. So what do the parameters look like on these? So on the northeast and the west, and I show northeast and west. Actually, we have no windows on the west face, but the U factor of a 0.16 and a solar heat gain coefficient of 0.27. But on the south face, we had to sacrifice a little bit of U factor, so it's up to a 0.22 to get a massive jump in the solar heat gain coefficient to maximize our passive solar. Now, passive solar, again, going back to Deborah Rucker Coleman, architect who specializes in passive solar. We relied a lot on her book, The Sun Inspired House, as an excellent resource in modeling the overhangs for the south face. So, so this particular model allows you to input where you're located in latitude, the height of the windows, the distance between the top of the window and the bottom of an overhang, and then the length of the overhang. What we were trying to do was to design overhangs for every south-facing window so that in December, January, we were close to 100% solar gain in the house, and in June, July, we were blocking as close to 100%, so 0% gain. And you can see from the chart, this is ultimately the design that we used. We came, we achieved the results we wanted, 100% in December, between 8 a.m. and 4 p.m., 100% solar gain, and 0 in June, when the sun is at its highest arc. But you can see that and we'll talk a little bit more about this in our lessons learned, but the literal gray area are the swing months, March and April, September and October. And this is where you have to make some compromises, because it is not uncommon in our part of Colorado to have days that don't get above freezing in April. We have blizzards in early May, and likewise in October, it's not uncommon to have 78 or 80 degree days. And so the overhangs are not going to perform as you would want in those periods. And so that's where a lot of the work in operating a passive home occurs, is in those swing months. Let me also mention that we had we optimized the windows on the south face. We have 0 windows on the west face because that's a common source of overheating in passive solar homes. And we have 0 windows on the east face, and we have minimal windows on the north face, for the minimum amount needed for daylighting, emergency egress by code, and also ventilation. I've mentioned a number of times the thermal mass on the main floor was the 4-inch concrete slab. We did not want to put concrete, obviously, on the second floor for engineering reasons. The thermal mass on the second floor, I went with a thermal mass in the vertical by doubling up 2 layers of 5/8-inch drywall and using that 1.25-inch gypsum as the thermal mass in the upper floor of the house. Let me also mention, in this book, The Sun Inspired House, there are some rules of thumb that you want to use. One of them is you want to use about between 5% and 12% ratio of the the glass area on the south face to the floor area. We were somewhere in the middle of that range, and we came in at about 8.7%. But the tighter you can make the house and the more insulated you can make the house, the lower this percentage can be because the less work uh, you need from the passive solar heating. So this is what it looks like. The south facing windows, the thermal mass, the concrete slab right after it was stained. This passive solar wall is connected to wood shop and garage, and is outside the thermal boundary of the house. So this is a completely passive solar wall. It's about 8 inches deep. Halfway through, there's this black painted perforated aluminum panel. Uh, Cold air is drawn into some ducts at the bottom, follows a serpentine route, gets heated up to about 140 degrees, and just through convection, that hot air then is put into the workshop and the garage. And so this passive solar wall provides all of the heating in the winter for those two rooms. Air leakage. Air leakage was the only graph that is purely linear just by the nature of the equation. The the greater the leakage, the greater the annual energy use. We were shooting for a target of um, 350 cubic feet per minute at 50 pascals. So for people not familiar with blower door testing, North American standard is to create a pressure difference between inside and outside of 50 pascals. That's the standard. And then you measure the the airflow, which would equate to the amount of leakage in the house. And that's what the ELA is, an effective leakage area in square inches. So 350 CFM 50 would equate to just something under 20 square inches of effective leakage area. So for the shell, we followed standard passive house guidelines and minimized any penetration through the shell. So our range hood is recirculating. It's not vented to the outside. We use ventless clothes dryer so that there's no clothes dryer vent to the outside. The spray foam use we maximize through the shell, and before the fiberglass was blown in, I did a blower door test on the house with the thermal camera to look for any leaks coming through the spray foam, and we were able to touch up about 5 or 6 places. So those were the techniques we used to drive the air leakage down as low as possible. And we did pretty well. So we actually beat our goal and measured 280 CFM 50, which is equivalent to 0.4 air changes per hour at 50 Pascal. And I'll point out that at the time in 2010, when we were in construction, our area had no code, no building code that required a certain level of air leakage like we do now. So this was testing that was kind of unheard of in our area of Colorado. Supplemental heat. It was interesting because the modeling was showing that we needed something really tiny in terms of supplemental heat. But the regional building department did not necessarily agree with that assessment. It took a couple of trips to them with the modeling results from Energy 10 before they would even approve to have the sole source of mechanical heat in a 3,200 square foot home to be uh, a mini split heat pump with just a um, single inside unit. Uh, and that heat pump is rated, let's talk about 17-degree Fahrenheit at 6.7 thousand BTU per hour. This particular Mitsubishi unit is a cold climate Mitsubishi, so it's actually rated all the way down to -5 degrees Fahrenheit. Although the performance drops, the coefficient of performance drops below 3 when you get down to 5 degrees. So that is the sole source of mechanical heat for the house. You say, well, how does a point source on the first floor heat the whole house? Well, we put transfer grills between all the rooms, so all of the bedrooms, bathrooms are connected through transfer grills. And also the ventilation system moves air through the house. And if you have a tight enough shell, you don't get isolated cold spots. And so you get fairly even heating, like within a couple of degrees throughout the whole house, just with a single point source heater. And we do also have a wood burning, high performance wood burning stove. Passive cooling. The central staircase was a thermal chimney. We have windows at the top of the staircase, and then small awning windows down below, and just using chimney effect, thermal convection. The heat would rise at night, go out the windows, and draw cool nighttime air in through the lower windows. Our energy recovery ventilator also has an Econo cool mode, which turns off the heat transfer function. And so if we have to use the mechanical ventilator in the summer, that also provides some cooling. And as we mentioned earlier, the overhangs work well, but the shoulder months are the ones that are probably more challenging than other months. The ventilation system is a energy recovery ventilator, which transfers between 80 and 82% of the heat energy in the stale outgoing exhaust air to the incoming fresh air. We also added a 100-foot long, 10-foot deep earth tube to preheat the air in the winter, because at that depth, the constant temperature of the earth is 51 degrees Fahrenheit. And also, if we needed it in the summer to pre-cool any air coming into the ventilation system. So that runs 100 feet to the house, comes up through the concrete floor, and then up into the attic where the ventilator is. Domestic hot water uses, it's a simple drain back system. So it's atmospheric pressure. There's no antifreeze in the system. 3 sun-earth collectors going to a drain back tank in the attic, and then on the main floor is a 120-gallon storage tank. And this system has worked extremely well for a family of 4. Okay, lights and appliances. Everything that went into the house was Energy Star. We have all LED lighting now, but LED lighting was expensive and not readily available when we started planning in 2009. So we started off with with compact fluorescents, but we've since transitioned. Um, Other items like a soft start, variable speed water well pump. We're on a well here in a septic system. Um, it saves a lot of energy. Uh, an electric induction stove with an induction compatible pressure cooker, huge energy savings when you can cook a pot of rice in 12 minutes. Same with beans, vegetables in about 2 minutes. You save a lot of energy with the pressure cooker. Um, but just taking a look at the load analysis over 12 years, just take a minute to talk about these. So um, over the first 12 years that we moved in the house, the house was averaging about 343 kilowatt hours per month. Uh, the or 4113 kilowatt hours per year. The electric vehicles actually consumed more, even though we didn't get the first one until we had already been in the house for a year. That the average over 12 years was 4358 kilowatt hours per year. We produced over 106,000 kilowatt hours of photovoltaic production. In 12 years, 4,400 of that was net excess. Um, and our space cooling was zero because we're using passive cooling 100%. And space heating using the mini split was turns out to be only 4.8 kilowatt hours per year average because the passive solar has worked so well on the house. Here's what the photovoltaics look like. We started off with 20 relatively small panels, but they were state of the art at the time in 2010 on the roof. And then when we purchased a second electric vehicle and got rid of all of our gasoline vehicles, we added another 8 panels in 2018 of a ground mount system. Water conservation, we the WaterSense program had not been formalized, but EPA had published draft WaterSense specs, and we built to those draft specs. We don't use any outside irrigation. We have a xeriscape outside plus 2 rain gardens, one for vegetables in the back and one just for decorative plants in the front. On-demand hot water recirculation pump. Every bathroom and the kitchen sink have a push button next to it. When you push the button, the pump will circulate the hot water through the whole house back to the hot water tank until it senses a 15-degree temperature rise, then it shuts off. We found these really cool Caroma dual flush toilets that have an integral hand washing sink that when you flush, the clean water coming back in to refill the tank is where you wash your hands, and then the tank is using gray water for the next flush. Sustainable features. We're almost done here. I want to make sure I leave enough time for a question and answer, but we minimized we reused everything on the construction site that could be either reused or recycled. Every piece of cardboard was recycled. Untreated lumber was chopped up and plowed into the soil. Gypsum from wallboard was ground up and plowed into the soil. So we ended up this whole construction program with only one dumpster load of debris being taken away, and that was mostly treated lumber and plywood that could not be burned or ground up. We used recycled material from the Habitat for Humanity Restore in terms of floor tiles. We built our own countertops with concrete and 650 pounds of broken glass bottle of different colors and sizes that we used as the aggregate when we poured these. Um, we had a local countertop company that allowed us to dumpster dive and pick up scraps of granite from their dumpster. And for indoor air quality, we avoided any products that had added formaldehyde or a lot of VOC off-gassing. So water-based paints, dyes, stains, polyurethane was used throughout the house, solid cork flooring. The solid interior doors are no added formaldehyde doors, etc. So indoor air quality was very important to us. And this was our first electric vehicle. In April of 2012, we got a Nissan Leaf because we were generating a lot more electricity than we needed just for the house. So let's talk about results. The modeling results looked really good. The house actually performed better than the modeling results. So this zero line right here separates energy consumption at the top and net excess production at the bottom. And the difference between the baseline high performance reference home and what the model said we would get with our house was pretty substantial. But let's just jump right to this, because this is the most important results chart. Since this is an all-electric house, grid tied, the single best measure of the performance is the net meter from the day that we moved in. These are all actual meter readings that we've captured. From the day that we moved in May 2011, everything above this point would be net consumption. Everything below this point is net excess. And you can see that the net excess was pretty steep until we reached the point of getting our second electric vehicle. Started to climb back up. This was where we added the second ground set of PV panels in our ground mount array. And this was interesting here. This range of this pink arrow was when the pandemic hit and we were not driving kids to school. We were not driving kids to sports. And so not using the electric vehicles, our net savings, our net excess production really became substantial. So at the end of at the exact 12-month point, we ended up with 4,400 kilowatt hours of total excess production. That's for the entire house and 2 electric vehicles. So lessons, and then we'll jump into Q&A. There's probably no more important element to start with in the planning and the beginning of construction than to start with the most efficient shell possible. It's simply the most cost-effective way to build a high-performance house is to minimize the thermal loss through the shell. So that means extremely airtight and highly insulated. So we have 2 rooms in the house, an office, actually the office that I'm sitting in now, and a bathroom on the 2nd floor that do not have any windows. And so I opted to put solar tubes in there, and I regret that decision. And the reason being is that the solar tubes require a penetration through our 18-inch roof and out through the metal outer roof, which was difficult and challenging to air seal as compared to the minimal amount of cost and electricity that modern LED lights would use. So in hindsight, I would just put LED lighting in and skip the solar tubes altogether. If I was building the house again today, I would really question whether to use a dedicated solar hot water system versus adding more solar PV and using a heat pump water heater, which did not exist when we were designing the house. But we're using these heat pump water heaters. I work with Pikes Peak Habitat for Humanity, and we're building all electric homes, and we're using these the Ream, your sponsor, heat pump water heaters, and our families love them, and their utility bills are still extremely low. Um, the problem with the solar hot water system is I throw energy away in the summer. When at 1 or 2 o'clock in the afternoon, when the tank reaches its maximum temperature of 168 degrees, the system shuts down, and so I'm not capturing any more energy. If I was doing this with a heat pump water heater and additional PV, then that additional electricity that I'm generating, that excess could be used elsewhere in the house. So that's something I would consider today. This was the right choice in 2009 for cost reasons and lack of heat pump water heaters, but probably not today. Um, Low iron glass on the south face to maximize solar heat gain also has a higher transmittance of ultraviolet. And boy, did that become apparent within the first year when we were getting fading of the flooring and fading of the wood trim around the window boxes. So that's been a constant struggle, is all of that extra UV causing damage. Um, I would have put more operable windows in. My thinking at the time was, hey, we have a mechanical ventilation system, so where I don't need an operable window for egress, we'll put in a fixed window. But it turns out that there are a lot of very comfortable days in the swing months where we turn off the ventilation system and just open windows. And so I wish I had more operable windows. Um, Finally, we installed but have never used a water to air heat exchanger that connects to our 120-gallon storage tank at one end, and the heat exchanger in the inlet um, be, to uh, the energy recovery ventilator, and the connection um, to the earth tube. Where the earth tube comes into the house, we put this heat exchanger. The thinking at the time was we could take excess hot water in the winter and preheat the air even more before it goes into the ventilation system. But it turns out that 120-gallon storage tank is not enough to do that. I would need to be almost double or triple what we have in order to have enough stored energy to provide domestic hot water and to provide additional space heating. So, conclusions: passive house works. The house has outperformed our expectations and the modeling, and we are, even 13 years now later, amazed just at how little um, we have to turn on any kind of supplemental heat in the house. And the construction was not difficult. None of our contractors had ever done anything like this before, and all of them said it was not a challenge to them at all to shift to this way of thinking. And the cost for those interested, our builder said we came in we at about 7.8% above his um, narrow window of what his usual price per square foot is for the homes that he builds. Um, and that was after the solar tax credits that existed back in 2010. With that, we are ready for questions. I'm sorry I ran a little long there, Brett.
No, that's all right. We still got time for some questions. And for those of you who need to get going and you've been here the whole time, you're approved for your CUs. But if you want to stick around for us with us to go over the questions. We'd love to get to your questions and hang out to answer more. So before we get into those questions, real quick, just a reminder, this session is being recorded. It'll be hosted up on our YouTube channel. You can go ahead there right now, click on the link. You can click subscribe and you'll get an instant update when it's available. Otherwise, those of you watching this in the future, make sure to take your quiz with an 80% passing rate. And for those of you here live today, check your spam for certs at gutenbergcerts.com, and then go ahead and take the survey that pops up at the end of the session. And before we get into the questions, again, a huge thanks to our board of directors, our over 300 members, our volunteers, and all of our top tier sponsors who are helping with products that help meet many of these sustainability, decarbonization, and passive house goals. So, Jim, one of the immediate questions I'm kind of going to here is of interest on the earth tubes. And the specific question, just so I can pull it up here and have it right, was, well, the question was whether you had the air quality tested on those earth tubes, and the context for that question was the individuals just concerned about long-term bacterial growth in those.
Yeah. So, and we were concerned about that also. We went with a company that actually, a German company that no longer has an office in the U.S. anymore. So these aren't even available. But the earth tube is a PVC tube, but it has a silver lining, silver iodide lining on the inside that inhibits any bacterial growth. So it was a very specialized earth tube. If you remember that I mentioned the windows were one of two areas where I could not make an economic argument for the decision, but we went with it anyway. The earth tube was the other one. For the amount of energy that it saves, when I calculated it, I could never justify it from a return on investment. But we went with it just to really drive our energy consumption down as low as possible. So, in addition to the silver iodide lining inside the tube, it's a smooth wall tube, which reduces mold buildup and moisture buildup. It has a constant slope downward until it makes the bend up into the house, and at that lowest point, there is a drain. Now, to answer the question, though, we have done, other than radon testing, we have done no indoor air quality testing because with our ventilation system running at the prescribed rate for the house volume that we have, I'm confident that we're keeping our indoor air quality at a very good level.
Well, and I'm glad you brought that up, and I have another question to come back to that real quick. But on the earth tubes, just staying with that a second, there was some kind of question about earth tubes versus geothermal, and in this case they mean ground source. But let me add to that a little bit. Was there a conversation or a thought in your design stage of using ground source heat pumps, which I know were very popular back then compared to air source, versus using the mini split and the earth tube? Was there a conversation there?
I have done a lot of modeling for and what ifs for customers when I had my energy audit business on that exact question: should I put in a ground source heat pump system? And we did the same analysis on our house, and it turns out that the return on investment or the break-even point was somewhere between 80 and 90 years, and the reason being was the enormous cost of drilling either vertical wells or laying out the horizontal bed. So, it's hard. It was hard at the time to get a geothermal system for under $30,000 or $40,000, and it violated, for our house, it violated the passive house philosophy. The passive house philosophy is focus your efforts on making the most efficient shell as possible,
Right.
and then quote heat the house with a hair dryer. So rather than putting a lot of
Mm,
money into high tech fancy
mm.
ground source heat pump and HVAC system, you take a fraction of that money and make your shell as high performance as possible, and then heat much cheaper.
Yeah. And so, there were a lot of questions coming in about the modeling you used, and clearly, you know, over a decade ago, we didn't have all the modeling resources we have now. We have of course, the Whoopie passive program and the passive house planning package that do a lot of the things that you were showing. But I'm curious, I assume back then you're saying the HERS rating program didn't actually cover what you were trying to look for, the information you needed?
So I used that program because I was a certified HERS
Right.
rater at the time. So I used that
Yeah.
program just for big picture things,
Okay.
but it is not an
Mhm.
hourly program.
Right.
It does not hourly model, and so it could not capture the impact of passive solar.
Okay.
And that's actually one of the shortfalls of the HERS modeling on
Yeah.
passive solar homes is it doesn't capture the benefit
Yeah.
hour by hour of capturing ambient
Okay.
energy from the sun.
Okay. Now I will say, for those of you in the future, next month we will be doing the modeling software tools on passive solar, and we will be going over HERS. I think they have moved to an hourly rating system now, but even despite that, I think you'll see some limitations when we go through that, everybody, on other passive solar issues that come up. So, but I think they did move to hourly just for more of a time of use programming. So, yep.
Yeah, I used, and most raters were using rem rate at the time. I think a lot of
Yeah.
raters have moved away from rem rate, and
Right.
there's a different program
It's
now.
the
And
software. Yeah.
yeah, and I believe you are correct that just in the last couple of years, it does now include hourly modeling.
Hmm. So it sounds like the Model 10 software you use was allowing you to look at everything uh, individually, and then you were using the HERS rating to look at the home holistically. I'd be curious, did you notice anything that it looks like you kind of went with the individual approach, right? The systems approach to how you focused rather than the whole home approach. But did you kind of, looking at both of those together, did you come up with any other decisions?
No, I mean the focus was primarily using Energy 10,
Okay.
starting with the reference home and then comparing it with the parametric studies. And the modeling on REM rate I started doing as we got closer to actually having the house formally certified. Before I brought in I, because of conflict of interest, I can't rate my own home,
Right,
so I had to bring
right,
in
right.
another company to do that. But I wanted to see. Uh, I modeled the house anyway in REM rate just to see what it was going to do. But for the design purposes, it was almost exclusively Energy 10.
Right, energy 10. Okay. Um, the question was, didn't you have a thermal break between the foundation walls, capillary break, and stem wall?
Yes,
Yep. Okay. Maybe they just weren't seeing it in that small detail. So thanks.
that yes, that picture was tiny, but
Hmm.
between the footing, if that's what you're
Hmm.
talking about, between the footing, the concrete footing, and the
Yeah.
stem wall,
Hmm.
there was a painted on
Hmm.
capillary break to prevent wicking of water. Yeah.
Yeah. Um, there was another question just about how did you ensure there was no heat loss around the window frame? Maybe this is more based on, uh, you know, uh, I guess ensuring proper installation, right? Construction. Yep.
Yeah, so in addition to the rubberized weather wrap that is used now on windows,
Mm,
um, before the insulating team came in, I went around all the windows and added an additional layer of just
mm,
Home Depot spray foam.
Mm,
around any gaps between the rough opening and the window
mm.
frame itself.
Okay. So you did a little bit of a self-commissioning there of the system.
Yeah,
Yeah.
yeah. I was out here at least every other night with my
Mm.
cans of spray foam,
Okay.
catching whatever the contractors
Yeah.
missed.
Yeah, yeah. So you had a little bit of what does Habitat for Humanity call that? A little bit of sweat equity, right? Into
Sweat,
the
I had sweat equity in my house. Yeah.
Yeah, yeah, that okay, fair enough. Um, I was thinking about well, there's some questions here on resiliency, and I learned something new from you on the roof venting strategy, and clearly you're using metal roofs, which show to protect against asphalt shingles burning down in fires. On the photos you shared, I didn't really see any kind of like trees around the house from what I could tell, which I know is another risk. Is there any other fire resilience strategies you use? And to add to that, any other additional climate resiliency strategies, like such as winds or tornado or hail or anything like that?
Yeah, yeah. So a few. The siding of the house we said was either going to be fiber cement or stucco. We went with
Mhm.
stucco, much more resistant. And I mentioned
Mm,
the lack of any ventilation into the attic. There's no soffit vents where embers can be drawn in. The metal roof. The We keep the wood pile. For our wood stove, we keep that well away from the house. The only other thing that we did when we were in a prepare to evacuate order a few years ago was taking the propane tank from our grill outside, and I moved that well away from the house. So you also mentioned the lack of vegetation around the
mm,
house. We've planted some small trees and shrubs, but there is nothing large around the house, and we try to keep the grass cut
mm.
as much as possible.
Yeah.
Um, and it's an added worry for us
Mm,
because we don't have out in our little rural area, we don't have fire hydrants, and so fire department coming in to fight
mhm,
this has to bring any water they're going to use, and so that was a concern for us.
mhm. Um, so I don't. So I was thinking about air quality, and I'm specifically thinking about particulate matter, PM 2.5. And I had one idea, and then you just put another idea in my head for the question. And first of all, I was curious um, if so if you're not monitoring the air quality, all you have is your own anecdotal information. But I was curious about if you had recalled any kind of burn events, right? So I know when you cook with electric, you reduce a lot of emissions, but hey, I cook with an electric stove. I've burnt before. I've seen the PM 2.5. I've smelled it, and I know that the energy recovery ventilator personally just does not get it out. And then of course you have wildfire smoke. It sounds like maybe pouring into the area once in a while could come into the house. And so I guess what have you seen with this way your
Yeah,
system is? Have any information on whether any kind of PM 2.5 particulates have been in the house?
yeah. Let me start with the wildfire because we had 2 years after we moved in, what was at the time the most destructive wildfire in the state's history, and the perimeter was less than 6 miles away from our house. The air was so thick with smoke we could not open any windows.
Mm-hmm.
That was one of the few times we used the
Mm-hmm.
Econo Cool function on the ERV. And there are one, two, three, four layers of filters
Mm-hmm.
that from the entrance to the earth tube to where it comes out of the ERV. There's four sets of filters, and when we closed the windows and just ran the ERV, we were not sensing, although I didn't have any measuring equipment, we were
Right,
not
right,
sensing
right.
any more smoke in the house.
Wow. Interesting. Um, and then on the cooking side, do you feel that the ERV you have has been fine for any
Yeah,
choose cooking
we
oils or anything?
Yeah, because we have a recirculating vent that goes through a carbon filter.
Oh, okay. Okay.
So the hood, the range hood, recirculates, but only after it passes through a carbon filter, and then anything remaining is drawn out by
Sure.
the energy recovery ventilator.
Okay. Um, Going back to your, so it's kind of two questions on the wall systems and humidity and moisture durability. So maybe one question, well, the question is is there any worry about a closed cell foam system? Uh, is there no worry about having a wall system that breathes because you've got the closed cell foam? And then maybe, I don't think the technology was around, but there were other, interior substrates that folks are using now instead of foam to do that.
Yeah.
So could you speak to that a little bit?
Sure. So the rule for wall systems is they have to be able to breathe in or they have to be able to dry in one direction. So the standard rule is you never ever put a vapor barrier on both sides of wall sheathing, right? So you would never put exterior rigid foam outside of sheathing that you've sprayed closed cell foam on the other side because any moisture that does get through has no way to dry. So what we did then is our sheathing is able to dry to the outside. So we only have the vapor barrier, vapor impermeable barrier on the interior face of the sheathing, uh, and and that has worked very well in other homes. The homes that have catastrophically failed on the walls have typically been because moisture was trapped between two vapor barriers. The other thing we did too was we spent a little extra money, and instead of using oriented strand board OSB, which is a little more susceptible to moisture damage, we use plywood.
Mhm. Okay.
I think that was overkill for our dry climate, quite frankly, but
Sure, sure. Um, what about power outages where you are? I know solar power in and of itself doesn't, doesn't work when the power goes out.
mhm.
So is that just okay, or do you have a system in place to still allow some kind of critical load, or have you considered batteries?
We have and made the decision not to do it just from a cost standpoint for compared to how little our grid goes down.
Okay.
Uh, but we we did want um, the battery backup for one thing only, and that was the well pump. The one
Yeah.
thing we don't
Yeah.
like is losing fresh water in the house. So
Hmm.
when storm systems are in the forecast, we fill up a bunch of water jugs so we have fresh water, and we have captured rainwater outside for things like flushing toilets. The other thing we have now is one of our electric vehicles with a 135 kilowatt hour battery pack has 120 volt sockets in it, so we can run things like the
Hmm.
refrigerator from the car
Hmm.
now. But I don't have a 240 volt outlet in the
Hmm.
car that I could run the well pump.
Hmm. Um, and on the note of solar, I don't know if your utility has shifted to some of the time of use programs where they, try to charge you more, in the summer during the middle of the day and less at night. Have you uh, have you signed up for that and tried actually shifting your
Yeah.
solar to send during that time or anything like that?
Our utility does have a time of rate option.
Yeah.
It is not available to net metered
Ah,
customers. So
okay.
they only give us one choice and one choice only.
Yeah. Yeah. That makes sense. And I'm thinking of your overall, net zero usage and your chart, but then I'm looking at the wood stove you have, and I'm curious, was there ever a time when in the middle of winter your passive heating and mini split combined couldn't keep up and you've had to use that wood stove to maintain a good temperature?
Never in the dead of winter when the sun is low and the overhangs are allowing 100% of the sun to come through. So we
Mm,
hardly ever, except for ambiance, we hardly ever use the wood stove in December and January. Where
okay.
we do use the wood stove is when we have 4 days of 20 and 30-degree temperatures in April,
Okay.
where we're not getting the overhangs are blocking the sun. But I can tell you that just last winter,
Mm.
yeah, so 2023, we we finally finished the first cord of wood uh, that we bought in 2012 when we moved into the house.
Okay.
So
Okay. So very
so in
minimal.
so in
Yeah.
in 13 years we've been through one cord of wood.
Right, right. So it's a very minimal amount of carbon use there. So
Yes.
yeah. Well, that's great. And on the where was the question here? Um, sorry about that. I was trying to find the question I had that came up on that also came up on that note with solar. Oh, for um your additional solar that you added to the house, um, did you consider just putting it on the metal roof of the workshop as opposed to getting the ground mount array?
Quite the opposite. I wish I had built a house and put everything on the ground.
Okay.
Uh,
Mm,
attaching rails to a standing seam metal roof using the S plus clamps
mm,
is a little
mm,
difficult. You run the risk of penetrations through the metal roof. But most importantly, when we get snow,
mm,
I can walk
mm.
out with a broom and I can clear off the snow
Sure.
immediately from my ground mount system. And it may take 2 or 3 days for the snow to
Mm,
melt off of the roof system.
right.
So we
Mm,
had the space available with our lot. I
mm.
wish, in hindsight, I just put everything on the ground.
Got it. That makes sense. Um, and then the just kind of, and I think you spoke to this just a little bit. I mean, but you had mentioned that operating your home in the shoulder season to keep the passive solar benefits, and that there's a lot of work to that. Can you elaborate a little bit more on that? And have you looked at any kind of automated systems?
Didn't really look at automated systems. We were trying to keep the house as simple as possible. And by the extra work, I mean we my wife and I do something what we call banking BTUs. So
Yeah.
you look at the forecast 2 or 3 days, the weather forecast 2 or 3 days in advance, and if there is a snow or storm system moving in, then we'll open up all the blinds and we'll capture as much solar heat in the days before, a couple days
Yeah.
before, even if it means getting the house up to like 78 degrees.
Mhm.
And then we're trying to store as much as we can in our thermal mass and then to make it through. So it's those kinds of things. It's mostly for us, it's controlling the thermal insulating blinds manually
Yeah.
to either trap heat inside or get more heat in the house before, or in the case of a heat wave in October, it's keeping those shades down to
Mhm.
block the sunlight coming in when we know it's going to be 80 degrees for 3 consecutive days in October.
Okay. Um, a decade or so later, I'm just curious about some of your systems and how they've held up. I think of the mini split. Has it had to been replaced or repaired? The ERV. I've heard of the passive solar water heaters in the past. One of the reasons people don't like them is they sometimes leak. So, anything that stands out to you that you want to share on that, or
Uh, the mini split has been flawless, but in 12 years, we used it less than 25 hours.
sure?
But it's still working great.
Mhm.
Uh, we are on our third Solar Edge inverter. So we've had two inverters go out that were replaced under warranty for the solar PV. Um,
Mhm.
the solar hot water, knock on wood, has been working fantastic, and that is a big
Mhm.
risk to us because it's very difficult to find
Mhm.
anybody to repair those systems
Right,
when they do fail.
right.
Um, but so far, and I think part of the reason
Mhm.
for that is it's a simple drain back system and
Mhm.
not operating under pressure.
Okay.
So there's greater
Mhm.
resistance to leaks. What else? All of our appliances, the Energy Star appliances have worked extremely well.
Mhm.
The only we did replace our dryer, but only
Mhm.
because at the time the only ventless dryers that were available were these small
Mhm.
European size, like apartment size dryers. But now they've come out with full size, big old
Right.
American
Mhm.
uh,
Yeah.
heat pump clothes dryers, and so we upgraded to one of the full size ones. Yeah,
Yeah. I bought one of those European ones a decade ago, and not so great, but
yeah,
but,
very frustrating to have to do two dryer loads for every
yeah.
washer load that you're.
Yeah.
Yeah,
And you mentioned heat pump water heaters in place of solar hot water and extra additional PV. The kind of question that's coming in from, you know, um, here just to add to that is I think it is if your solar water heater were to go, have you seen or considered the sort of integrated heat pump water heater ERV systems at all? Have you seen anything like that or have you considered that?
I'm not familiar with those, but
Yeah.
that's something I will look into. That sounds like an interesting concept.
Yeah. Yeah. Yeah, I don't see them too
Do
often,
you
but
know who makes those?
I don't know. I don't. And if our guest wants to share, it was their question. I was just kind of following up with that.
Okay,
I've seen systems that have been two different systems and they've been engineered together, but I've never seen
right.
one individual ERV and heat pump, all in one. So yeah, but I'd be curious too to learn. So if they want to share it, feel
I
free.
mean, the heat pump technology has progressed to the point where that would be, I think, a very viable concept.
Yeah, yeah. Um, Well, Jim, I think we're at the end of our session. We went over a little bit later, so I really appreciate you sticking around with us. I was wondering, do you keep like a blog or any updates that you share out on your house that people could follow if they wanted? I mean, clearly they got 12 years worth of information here, but
Yeah,
I didn't I didn't know if you've done anything like that or have anything
Uh,
like that.
I don't. When I was sitting on the board of the Southeast Colorado Renewable Energy Society, we would have a lecture series, and I would provide every couple of years. I would provide an update on the house, but that was in the form of either a webinar like this or a live presentation. But no, I don't have a blog. But I will say, Brett, if anybody has any specific questions, feel free to provide them with my email address. I'd be happy to answer any
Okay.
questions directly. I may
Okay.
regret saying that because you had a large audience here, but but no, I always enjoy talking about this, and I'd be happy to help anybody with any questions.
Great. Yeah, we will share that out. So, Jim, well, I appreciate your time. Thanks for joining us and sharing this and putting this effort in, and hopefully it inspires others to do the same. So, thank you so much.
My pleasure. Thank you for inviting me.
Okay, take care, everyone. We'll see you next week. Goodbye.
Bye bye.